Right now, thousands of miles above your head, an invisible mechanical network is quietly running the modern world. If those satellites suddenly shut down, the effects would be immediate. Global supply chains would freeze, financial markets would lose their timing signals, halting trading, and the GPS network that guides everything from commercial flights to your food delivery would vanish. When we picture that orbital environment, we tend to imagine something serene, a vast, silent vacuum where satellites float miles away from anything else. That quiet image is a dangerous illusion. Earth's orbit is actually a congested, highly volatile highway, heavily populated by moving hazards. The primary danger up there is the sheer speed required to keep objects from falling out of the sky. To stay in low Earth orbit, everything must travel at roughly 17,500 miles per hour. At that velocity, the rules of kinetic energy amplify mass into extreme destructive power. A single stray bolt floating in orbit hits a target with the explosive force of a modern hand grenade. When those micro-projectiles strike, they punch right through structural metal. Even flakes of paint traveling at orbital speeds carve deep craters and tear violent punctures through the vital foil shielding of multi-million-dollar spacecraft. Left unchecked, one major hypervelocity collision produces thousands of new fragments. Those new fragments hit other satellites, creating a runaway chain reaction that could shred our entire orbital infrastructure. Space agencies around the world are actively pooling their resources to manage the escalating chaos above us. But their defense strategy relies on a rigid physical limitation. Operators cannot protect a satellite from a threat they cannot track. To find those hazards, they built a massive Earth-based network of radar and optical sensors. These stations sweep the sky continuously, measuring the radar cross-sections of tiny, fast-moving objects. This animated map shows how they combine those global data streams. What you are looking at is a real-time catalog of millions of fragments, plotting the extreme density of the debris field. Knowing exactly where the hazard is provides vital situational awareness, but a map cannot physically stop a piece of jagged metal traveling at Mach 23 from striking its target. When the tracking data confirms an incoming threat, the operators execute a collision avoidance maneuver, their primary active defense protocol. Computers run predictive calculations against the orbital map. If a tracked piece of debris and an active satellite will enter the same narrow red zone simultaneously, alarms trigger. Operators must command the satellite to fire its thrusters, pushing its orbit out of the collision path. It works, but it comes at a steep cost. Evasive burns consume limited, irreplaceable fuel and interrupt the satellite's primary mission. And this tactic is entirely useless for the many thousands of dead, unsteerable satellites still circling the planet. Dodging is a temporary fix. Trying to outmaneuver a constantly multiplying swarm of debris is a battle of attrition we are mathematically guaranteed to lose. To prevent the total lockdown of Earth's orbit, space agencies have to transition from passively dodging the debris to actively hauling the largest pieces down. Engineers are testing specialized hunting satellites designed to match speed with the dead weight, deploying nets or robotic arms to physically grab the wreckage. Once secured, the hunter satellite forces both itself and the captured debris into a steep dive. The friction of atmospheric re-entry acts as an incinerator, burning the mass up safely over open ocean. Perfecting active debris removal moves humanity away from mere survival tactics, giving us the tools to perform actual, large-scale environmental cleanup in space. Cleaning up this orbital junkyard secures our unmanned infrastructure, but the stakes are much higher for human beings. A dense, unmanned debris field turns the upper atmosphere into a physical barrier. A single high-speed strike on a pressurized crew cabin means instant, catastrophic failure and the loss of astronaut lives. Every future mission to the Moon or Mars relies on a vehicle that must first safely punch through this congested orbital shell before it can head into deep space. Solving the debris crisis is the absolute prerequisite for the future of spaceflight. If we fail to clear the path, we risk building a steel cage around our own planet, trapping humanity on Earth.